So on this last handout that we worked on, we came up with an expression that we think is measuring the direction of circulation of a vector field around any given point. If you plug in the point you're interested in, the sign of this will tell you which direction the vector field is circulating around that point, or whether it's circulating at all. Right? You might get 0. And also, I mean, if we've done things right, the larger this number is, the more circulation there should be. So as you can imagine, that this is an interesting quantity in many situations involving vector fields, and so we'll give this quantity a name. Circulation would be a perfectly good name, except, I don't know, it's too many syllables for mathematicians or something. So instead of calling it circulation, it gets called curl. So if we have a two-dimensional vector field m comma n, the curl of that vector field is exactly what we came up with before, partial n partial x minus partial m partial y. And again, the reason that we care about curl is when this is positive, the vector field circulates counterclockwise about the point. If we plug in a point and we get a negative number for curl, then the vector field is circulating clockwise around the point that we plugged in. And of course, if it's equal to 0, then there is no circulation at all. I don't know how to draw that. I'll just draw a dotted circle. So let's work this out for a couple of examples. So for each of these examples, we'll calculate our expression for curl. So for this first one, partial n partial x, right, taking the partial of minus x with respect to x, that's minus 1, minus, don't forget this minus sign, partial m partial y, and that's going to be 1 in this case. So we get minus 2. And so this vector field, according to our calculation, this vector field is circulating in the negative direction at every point. Based on the graph, it's definitely circulating in the negative direction at the origin, since everything is sort of circulating around the origin. But even at points away from the origin, it looks like it's circulating in the negative direction. For example, if we look at this point up here, points just above the vector field is going rightwards more than points below are going rightwards. To the left and right, the vector field is sort of pointing through this point that we're plugging in, and that doesn't contribute to the circulation at all. And so this appears to be circulating clockwise, which, right, is what the calculation tells us. Something that the calculation tells us that is not at all obvious is that the amount of circulation isn't just always negative everywhere in the plane. It's actually always exactly the same, which is a surprising thing, I think. That's not at all obvious just from this intuitive reasoning about which direction this is circulating. If we calculate this curl for this vector field, well, this vector field is similar to the previous one. It's the negative of it. So it seemed like we ought to get the opposite sign for our curl. Let's just check that we do. Partial n partial x is going to be 1 minus partial m partial y, so that's going to be minus 1, and yes, indeed, we get 2. So if the last one had the same degree of circulation everywhere, this one should too. It's just the circulation is in the opposite direction, which is true because the curl comes out to be positive 2 instead of negative 2. Just like you can look at the graph of a vector field and estimate where the divergence is positive and negative, you can estimate where the curl of a vector field is positive and negative. So before we calculate the curl of this vector field, let's just see if we can estimate in general where the curl might be positive and negative. So if we look over at the right, say, at this point along the x-axis, it looks like to the right of this point the vector field is pointing up strongly, right? To the left of this point, the vector field is pointing up, but is very short, so up but weakly. Above and below, the vector field is sort of through the point, and remember, that doesn't really contribute circulation at all. And so at this spot, it looks like the circulation is going to be going counterclockwise, and so that would be a positive circulation. So let me erase this mess I made and just write a big plus here. So when the vector field is up and longer on the right, we should get positive circulation. But that is true here and here, you know, all of these places. It seems, maybe up to here, it seems like the vectors to the right are bigger than the vectors to the left. Okay, up here it's very hard to tell what's going on because the vectors are so small. Over here, well, now the situation is reversed and the vector to the left is still pointing up, but the one to the left is the longer one now. And so this is going to cause a circulation that's clockwise, and so that's going to be negative. So at this point we have a negative circulation. And if you think through the same logic at other points, right here, this vector is a little bit longer than that vector, so still a negative circulation. It seems like maybe about like this, we're going to have negative circulation. So something like this. In the middle here, it's kind of hard to tell what exactly is going on. So with all that in mind, let's actually calculate the curl here and see what we get. So curl of this vector field F is partial n partial x minus partial m partial y. Don't forget that minus sign. So let's see, partial n partial x, we're looking at this coordinate and we're taking an x derivative, so that's 2x, minus, and then partial m partial y, we're looking at this coordinate and we're taking a derivative with respect to y, so that's x. So what we get is x. So it looks like we have positive circulation when the curl, right, x here is curl of F, when this curl is positive, and we have negative circulation when x is negative. So it looks like the circulation is positive not just in this region here, but actually in the entire half plane to the right. And the circulation is negative in the entire half plane to the left. So you can tell, right, in some situations it's actually hard to tell whether the curl is positive or negative. But when the curl gets big enough, that's when we can actually tell whether it's positive or negative. So estimating curl, right, it's most effective when the curl is big, usually. So we, along the x-axis here, of course, the curl is exactly 0. Because along the y-axis, x is equal to 0. There are vector fields whose curl is 0 everywhere, and those are called irrotational fields, or irrotational vector fields. Of course, the name is just because if something, curl is like a rotation, and if it's not curling, then it's not rotating. So that's where the name comes from. And there are lots of vector fields that are irrotational. You might think that they're a rare thing, and they are kind of a rare thing, but one example is this one, so x comma y. Notice this is our radial vector field, our standard radial vector field, and you know, a radial vector field is like as divergent as possible, so it kind of would make sense that if it's as divergent as possible, it should curl. So it seems plausible that this isn't going to have any curl, but let's calculate. So curl of F, remember that's partial n partial x minus partial m partial y. So that's going to be this derivative, that's 0, minus this derivative, that's also 0. Sure enough, we get 0. Okay. In fact, you can see that it is pretty straightforward to come up with an irrotational vector field. If your m function is a function only of x, and your n function is a function only of y, that's guaranteed to be irrotational because, right, if m is a function of x, this derivative is going to be 0, and if n is a function only of y, this derivative is going to be 0, and so the whole thing is 0. But it turns out that there are other vector fields that are irrotational, but there's going to be a homework problem about that.